All right, we're going to talk about driving today. Um, so we have a silicon wafer. All right, this is just one dimensional. This is the top of the wafer. This is going down. That's X. This would represent the silicon dioxide. And when you implant, you get what is almost a two-dimensional distribution, and in this case, boron. So I've just drawn it like a line. All right. And so this is a fixed amount of dopant. Now in this case, the background, the wafer, is also boron doped. So there can be no junction because we're going to have p-type to p-type, or I have boron diffusing into boron. So you can have a concentration gradient, but then as soon as you get to the background concentration, it doesn't change. All right. So um, the problem statement says it's between 1 and 10 ohm centimeters, and you need to know what the background concentration is in centimeters per cubic centimeters. So I don't know, in my books I have a chart, but if you don't have a chart, you can go to the BYU lab resistivity and mobility calculator. I click on boron, and this is for silicon. And yeah, I just entered in doping concentrations and calculated until I got the ohm centimeter, right? Maybe there's a way to do it the other way. But so 1.16 times 10 to the 16 gives about 1 ohm per centimeter, and 1.5 times 10 to the 15 gives about 10. So you can just Google that, and it's right there. Okay. So so let's just look at what that means. So after drive-in, which is Gaussian because it's a limited source of dopant, right? We put in a limited source of boron. If um, if we had an unlimited source of boron out here that never ran out, that would be an error function. All right, so you would never, for drive-in limited source, it's always a Gaussian distribution. Now, the blue line would represent the nominal resistivity or background concentration. 1 ohm per centimeter was about 1.6 times 10 to the 16th. 10 ohms is about 1.5. All right. So you can see that this depth and it's not a junction depth, it's really where the diffusion curve equals the background concentration. Right? You can see that it would get deeper the lower the concentration. Right? The important thing for this step, though, it's not in the question, is the surface concentration, because that's what determines the threshold voltage of the device. So the devices come with dopings that are so low that the transistors will be normally on. We want the transistors to be normally off, or you have to apply a voltage to turn them on. So we do an implant and then drive it in to raise the surface concentration. Right. If it were 1 ohm per centimeter, it might work, but 10 ohms per centimeter, it'll be negative threshold voltage. And so I can't guarantee that range. You just buy it between 1 and 10, and you use this implant drive-in step to get that to work. Okay, so coming back to the question, yep, that's the resistivity. Now you know how to convert that into doping concentration. Orientation doesn't matter. The cleaning doesn't matter. The oxide screening thickness in this all determines that initial dose or the amount of dopant to begin with. right? So in order to have a drive-in, you need time, temperature, and how much dopant is already there. Then you just look up the diffusion constants and calculate, right? Which, to save time, they've given you the constants here, which you plug in with 1025 and 60 minutes. Of course, you got to convert that to Kelvin, right? Um, Determine the theoretical drive-in depth using this calculation, right? So the assumption here is that the background isn't changing that much, right? Um, in our case, we're using solid, I don't know, it shouldn't affect it at all because we're just flowing nitrogen and we've capped it with silicon dioxide, but whatever the professor says. So hopefully that explains how to do this problem. Let me know if it doesn't.